in my friendship. Don't people make experimental drills?
Huge.
No, not always. I debrief.
The best.
Okie doke, let's get started. We got a couple things to do today. We're going to start by debriefing with what we talked about on Friday, or actually what you worked on Friday. First things first, what's that equal to? Why?
Isn't there just a point or a vertical line, so there's no area below it?
Right, it's a vertical line, so it has no thickness, therefore it would have no area. That comes up quite a bit. Okay, that's the first thing. Second thing, as you start working through this worksheet, we found all kinds of fun things, right? And some of you are horrible at pattern recognition, by the way, because that's what this whole worksheet was about, is recognizing the patterns and noticing that T's become X's and all kinds of funny things happen. We're actually going to come back to this white sheet later. That's the second part of the fundamental theorem of calculus. But we're doing things backwards. I'm actually going to teach you the first part of the fundamental theorem of calculus today, but use the second part to talk about the first part, if that makes any sense. Okay? Well, we'll go with it. All right, so what did we learn from that worksheet? We learned that if we, let me get rid of this, because I don't want to confuse anybody. Okay, so you learned that if I do this, I get what? Well, first of all, what's going on there? The integral is what we call the area function. Right? So we have a fixed number, a. So whether it's 0 or 1 or 17 or negative 400. And then x is the variable. So we slide that along and we create this area function. And we start with the function f of t dt. What happens when I take the derivative of that area function? What do I end up with?
F of x dx.
Not f of x dx, just f of x. Yeah, because the dx, which is called the differential, goes away. Well done. Okay? Which makes sense. The derivative and the integral are opposite functions. It's just like squaring and square rooting. If you square a square root, you get back to where you started. You know? Same thing's going on here. But the thing to notice, which we'll cover when we talk about the second fundamental theorem of calculus in detail, is that variable change. And that's the thing that a lot of you didn't see, that we started with f of t, but we ended with f of x. We started with cosine of t, but we ended with cosine of x. We'll talk about that later on. Okay? So we know now that dy dx is equal to lowercase f of x. That's where we're going to start. Now we're going to do a little trick called separating the differentials. So these little guys, the dy and the dx, are called differentials, and we're going to split them up. I'm going to take this, and I'm going to move the dx over with the x, or the f of x, because that's where it wants to be. It doesn't want to be with the y, it wants to be with the x's. Basic rule of algebra. Whatever you do to one side of the equation, you have to do to the other side of the equation. So I'm going to take the integral of both sides. What's the integral of dy? Maybe this will help. What's the integral of 1 dy?
E over 2y squared.
Would it be,
Mm-mm.
would it be 1?
Mm-mm.
1. Why?
Why? Good. What's the integral of lowercase f of x?
Wait, how did you get y?
Because it's just the integral of 1. Like if you had the integral of 2, it would be 2y. If you had the integral of negative 7, it would be negative 7y. Okay, so we just got a 1 there, that becomes y. What's the integral of lowercase f of x? you have no idea what f of x is, right? So this gets back to our notation that we used at the very beginning of the chapter. What's the antiderivative of lowercase f of x? Capital F of x. But it's an indefinite integral, so we need a plus c. Okay? Which means that we know what, where are we going to from here? This gives me that this, x f of t dt, that's y, that's what we started with at the very beginning, that's our initial function, is now equal to capital F of x plus c. All right, so I just did a substitution that this guy is equal to y, because that's how we started the problem. We had some function that we defined as the area function. Okay so far? Okay, now what we're going to do is we're going to say, well, let's make x equal to a. Now why would I make x equal to a? Well, you'll see in a second. If I make x equal to a, then what does the left-hand side of this equation become? 0. Nope, sorry, I lied. That should be an a. Let me erase that. That should be a plus c. Okay so far? So what's c? Negative f of a. How are we doing so far? We are actually getting to a point in a second. Say again? Got it? Okay, now let's do it again. I'm going to change colors here, and I'll come over here. Now let's make x equal to b, just to change things up a little bit. Then we get the integral from a to b of f of t dt is equal to f of b plus c. Okay, so that's just a plug and chug. Which means I know what c is, because I solved for that here. And after everything is said and done, we get the following. Run out of space there. And that's kind of a crazy little convoluted way to get to the first part of the fundamental theorem of calculus. That is actually the fundamental theorem of calculus. And once everybody has that, I'm going to switch over to the slideshow and move on from the slideshow. So that's how we got there. We played with that area function, and like I said, we did things backwards. Instead of doing the first and then the second, we're doing the second, then the first, because I think it makes a little bit more sense. That's a lot more complicated than the actual application. The actual application is really easy. Are we good here? Okay, good. Get rid of that. Come over here. Start this. Okay. So blah blah blah. Yeah. Okay. Yeah. Hey, meet somebody new today. Okay. All right. There's the fundamental theorem of calculus. What does that mean? How would I do that? What am I supposed to do, Jimmy?
That to find the area of a function, you take the right and left endpoints and plug them into the integral. Or well, I guess, yeah.
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 Pretty well said there. We have an integral here. It's a definite integral. We're a and b. So remember, physically what we're talking about is the area under a curve from a to b. If I want to find the area under the curve from a to b, we looked at all the geometric ways to do that, which we'll talk about the green worksheet in a little bit. But this is going to allow us to do it without, for functions like I talked about the other day when we had x squared and you got this weird curve, you want to do it. it's real simple. You take the antiderivative, which is capital F, you plug in B, you get a numerical value. You plug in A, you get a numerical value, you subtract the two, you're done. Okay? So remember, capital F is the antiderivative. So you take the antiderivative and then plug in B, plug in A, and subtract the two things. So let's see that in motion. Okay, we'll do something real simple. Execute. Now, that's not something you're going to draw a geometric picture of. It's not a triangle, a rectangle, a square, semicircle. It's some weird looking function. You all know what x cubed looks like. So what do we do first? Take the antiderivative. What's the antiderivative of x cubed, Regan?
1 over 4 x to the 4.
Perfect. And so here's some notation.
Plus c.
No plus c.
No plus c?
Right. Okay, that's the other thing that I was going to get to in a second. There's no plus c anymore because we're finding an exact area under a curve. So here's the notation that we switch to. When I take the antiderivative of this, I get 1/4 x to the 4th or x to the 4th over 4, and then you either draw a segment or a bracket from 3 to 0. So that's the way of indicating that I took the antiderivative and now I need to plug in 3 and I need to plug in 0. By the way, did I tell you these are called the limits of integration? Did we talk about that already? Okay, good. Upper limit of integration, lower limit of integration. Okay. Plug in 3, plug in 0, subtract the 2, get your answer. Done. And it's just that easy.
Yeah. It's gonna get harder.
Second that.
It's not any harder. What's the antiderivative of 3 times the square root of x? What would you do first, Sid?
Oh, sorry, can you go back? I mean, on slide. presentation.
Oh, sure, sorry. I misunderstood.
Thank you.
You're welcome. If you were solving that antiderivative, what would you do first? Rewrite it as? Yeah. Not only would I rewrite it as 3x to the 1/2, I'd move the 3 out in front because I don't care about it. Doesn't matter. That way I don't get confused when I'm doing fractions and stuff. Boink. Whoa, that's a whole bunch on one click. All right, so rewrite it 3 times the antiderivative or the integral of x to the 1/2 from 4 to 1. The antiderivative of x to the 1/2 is 2x to the 3/2 because I multiplied it by 3 to get rid of that. Plug in 4, plug in 1, subtract the two values, 14.
Is it just units? Or units squared?
Yeah, it's usually just units. Unless the problem specifies, like we'll get to some word problems later, way in the future.
Yeah.
But otherwise it's just units. Pretty good time.
Does that 3 in front even matter? Or?
It does because when I raised this by 1 to get 3/2 and then multiplied it by 2/3, the 3 and the 3rd cancel. That's why it's just a 2. Now you could leave the 3 out in front, do this whole business, get an answer, and then multiply it by 3 at the end. It's entirely up to you. It actually, this one works out nicer because you get rid of the fraction early on. Okay. We got it? Pretty simple concept. So the stuff that you did Friday, like I said, does the second fundamental theorem of calculus, and then we can build up to the first one. And then the first one is just an application of the actual mechanics of finding those antiderivatives. Okay, it gets a little harder. I'm sure you all remember what the antiderivative of secant squared is, right? I'm sure somewhere in your notes you have the antiderivative of secant squared written down.
Yeah.
Are they good?
Tangent?
You sure?
Yeah, I'm positive.
Can somebody confirm? It is tangent. So then it is just tangent evaluated from pi over 4 to 0. Tangent of pi over 4 is 1. The tangent of pi over 4, sorry, the tangent of 0 is 0. 1 minus 0, 1. Now, the only thing that's going to get more difficult with this is sometimes the functions will be a little bit more complicated. But the process stays the same. Take the antiderivative, plug in the upper limit of integration, plug in the lower limit of integration, subtract the 2, and you get an answer. Okay? Are we good? Anything confusing about that? Let's talk about one last example here. That guy. What happens when you put an absolute value around a function? You cry, and then also. All right, get out your calculators. Graph that function without the absolute value. So graph x squared minus 2x minus 3 on your calculator. Again, without the absolute value, let's not spoil the fun. It's a parabola, right? That opens up. Where's the vertex? Is it below the x-axis? Yeah. So when I put the absolute value bars around that parabola, what's it going to do to it? Josh?
It's just gonna move it up, like,
Be more specific.
it's gonna flip it over the x-axis.
Not the whole thing.
Not the whole thing, just the part that's under.
Beautiful. Anything that's below gets flipped up on top. Everybody with me so far? So it's going to look like that. What you need to know now, though, is where these points are. Why do I need to know those points? Well, let's suppose we just did the integral from, well, you have fn int on your calculators. Do fn int of that without the absolute value bars. Excuse me. So go from -2 to 3 of x squared minus 2x minus 3 dx. Without the absolute value. Got a negative answer. Hold on, let's confirm. Can somebody else tell me what you got? Negative 3.3333333? Okay, so hold on, let me back up. We took a parabola, found the area under the, we found an area, and the area is negative. Have you ever heard of a negative area? No. So where did we screw up? We didn't add the absolute value sign. Okay? Add the absolute value sign. Let's see what we get. See if that changes the answer. I would hope it would, but the easiest way to get to the absolute value is catalog, and it's the first. So catalog is above the 0. So second 0, ABS is the first choice. And then that creates parentheses. You put, blah blah blah. But this is AP calculus, so you got what? 13. Okay, good. How do you explain the difference? Why is one answer, when this is back down here, why do you get a negative answer, but when it's up here you get a positive answer? So below the x-axis, why would that give me a negative answer though? And so you're saying, is anybody else bothered by the concept of negative area? Yes or no? Yeah, because it doesn't make any sense. So we need to come up with a way to explain how that happens. Well, let's finish this problem first, then we'll come back to this. I've got this. Okay, I broke it into a couple different parts here. And I started going from -2 to -1, and then I went from -1 to 3. Okay. Why would I do that? Well, that's the part that I had to flip over in order to get a different value. Okay, so notice the difference in the functions. Here I started with the original function, but then I multiplied everything else in the second one by -1. Why? Because it's below the x-axis, and I don't want it below the x-axis. I want it above the x-axis because it's flipped over. And I don't know how to take the integral of an absolute value. So instead of doing the integral of an absolute value, I break it into two things that I can work with. I can work with the region to the left of -1. I can work with the region to the right of -1 just by flipping it over. And then you can, I'm not going to finish by going through that, but it does lead into a nice segue about negative area. So let's suppose we have the following. Let's do, okay, let's do that, and we'll go from -2 to 2. So I'm wondering, what is the integral from -2 to 2 of x squared dx? And just to save time, go ahead, FN into it, tell me what the answer is. For those of you that are visual learners, we're looking for the area here and here. And that's approximately equal to 5.333. And we could practice doing that by hand. We would get 1/3 x cubed evaluated from 2 to -2. Plug and chug, blah, 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 5.333. Or whatever that would be. It would, 5 1/3, which would be 16/3, I think would be our exact answer if you convert that back to a fraction, right? Does it convert back? So math enter that one. I like it. 16/3 is a little cleaner. Okay, everybody with me? Just practice. Now let's change it. Instead of doing x squared, let's make g of x the opposite of x squared. What is that going to do to the graph? Flip it. Flip it over the x-axis. So we're going to get something that looks like this. And now we're going to have a region down here. So this would be the integral from -2 to 2 of -x squared dx. Go ahead and do that one for me. -16/3. And I'm eventually getting to a point here. You'll recall in one of the previous examples I did, we had a 3 floating out in front, so I can just move the 3 out in front, do all my calculations, and then multiply my answer by 3. I could have solved this problem by doing it the following way. I could have just moved the minus sign out in front. We know what this is, because we solved for that over here. That's our 16/3. Then you multiply your answer by -1. After all of that business, what have we learned? We have a new concept, and that is any area that falls below the x-axis now all of a sudden generates a negative area. Okay. So what if I looked at something bizarre like this? I had this curve that went from this blue curve, and let's call that blue curve h of x. What if I did the integral from -2 to 2 of h of x dx? What would that give me?
0.
0. Very good. Why, Greg?
You take half of the integral of f of x and half of the integral of g of x, and just you add them together and it's 0.
Good. Okay. Another segue. Instead of doing what Greg just described as he didn't do the integral from -2 to 2, he did the integral from -2 to 0, and then from 0 to 2, and added those two up, right? Okay, so that leads us to this. he could, he went from -2 to 0 of h of x dx plus the integral from 0 to 2 of h of x dx. And that still gave us the same answer. The area above is the same as the area below, they cancel out. So that leads us to, whoops, no, wrong button. This one. If we have an integral from a to b of f of x dx, you can rewrite that as the integral from a to c of f of x dx plus the integral from c to b of f of x dx. Does that make sense? If I'm going from a to b, I don't just have to go from a to b. I could stick a c in there and say, okay, I'll go from a to c and then from c to b. One last thing, and then we'll talk about the green sheet and the yellow sheet. What happens when b is smaller than a? So every time we set up an integral, we want it to be where b is greater than a. But what if it's backwards? How do you handle this? Any guesses? Michael?
Is it just the answer from 2 to 4 but negative?
Yeah. Anytime you need to switch the limits of integration, you just stick a minus sign in front of it. Okay, so the integral from a to b of f of x dx is equal to the integral from b to a of f of x dx with a minus sign in front of it. Okay, when you flip the limits of integration, you just stick a minus sign in front and you're good to go.
So when you used rectangles, you got like a range, obviously, because left-hand has
Sure.
Is there any comparable way to get the exact area like there is with this, but with rectangles?
With rectangles,
Yeah.
yeah, you have to do it as a limit. We kind of skipped that concept because it means going back to this.
It's fun.
Yeah.
Yeah.
And that's about 3 days worth of work because there's a bunch of
infinity
sigma
rectangles
notation formulas that you need to know,
Yeah.
and then you play with all that, and it's not worth it.
Yeah.
Okay. So the only thing you need to get out of it is the fact that you make delta x really, really tiny. The rectangles get really, really small, and then eventually when they go to 0, you get an exact answer.
Right.
But now that we have the first fundamental theorem of calculus, we can find the exact area using that idea. Okay, we doing good so far? Any problems there? So a lot of it is just mechanics stuff. Putting functions together to get one integral, or taking one integral and breaking it apart. You saw that on one of the worksheets, which we'll talk about in a second. What happens when the b and a are not the right order? You know, smallest on the bottom, biggest on top. If it's wrong, flip it over and change the sign. Okay, so we're good? All right. Let me get rid of this.